I will talk about cyclic systems in some detail, but before doing this, I would like to go over some basic aspects of the general approach to contextuality that I have been working on, for several years now. It is called contextuality by default approach, and its object is a set or system of random variables, which are classified in two ways: by their contents, and contents are simply the properties that these random variables measure, or another way of looking at it, questions that the random variables answer. Now, I will confine my presentation to yes/no questions, meaning that my random variables are binary, and it is, of course, a loss of generality, but within the framework of contextuality by default approach, it is actually postulated that we have to dichotomize the variables before we subject them to contextuality analysis. And the reasons for that will be presented later today by Jana Kujala when he speaks about the dichotomizations and principles guiding them. Now, the second way in which random variables are arranged is by contexts. It's simply the conditions under which certain set of random variables is being recorded, and this forms a system of random variables that is being analyzed. Now, within each of the contexts, we have several random variables referred to as bunches, and they are jointly distributed. So, for example, these red-colored random variables are jointly distributed, and these are jointly distributed. But if you take two different bunches in different contexts, then they have no joint distribution between them, and they are stochastically unrelated in our terminology. Now, another way of kind of arranging the random variables are in columns, so according to which question they answer. So, for example, these three random variables, red colored now, they answer one and the same question, and these two random variables answer the same question. So the random variables within a single column are referred to as connections in our conceptual framework, and this allows us to classify the systems into consistently and inconsistently connected. So if you take two random variables within a connection, so answering one and the same question, and if their distribution is one and the same, we speak about consistently connected systems. And if it is not necessarily true, so it is possible that for some two random variables, the distributions are different, then we say that the system is inconsistently connected. It roughly corresponds to disturbance, no disturbance, although disturbance sometimes can be defined in a more constrained way than just consistent connectedness. But because I'm not assuming consistent connectedness to begin with, I don't have to get into stronger versions of non-disturbance. So the definition of contextuality is based on a slightly different idea than the one that's usually being presented as justification for contextuality. Although you can always relate it to hidden variables with non-contextual mapping and other things, but the general logic of defining contextuality is based on comparing random variables answering the same question and comparing them in two different ways. First, taken in isolation and then taken within context. And the difference between these two differences is actually what is being reflected in contextuality. So let's say that we have taken these two random variables answering one and the same question, and we have taken that in isolation, so we have forgotten about all other random variables. Then the way we treat this we are creating their distributional copies. So it is X, which is distributed as this random variable, Y that's distributed as this random variable, but this time we are assuming that they are jointly distributed. This tilde here replaces the words is distributed as. So these are copies, and JD here refers to the fact that X and Y now are jointly distributed. There is an infinite number of ways in which you can create this X and Y, and we are constructing the one such that the probability with which X equals Y is maximal possible given their individual distributions. This probability is uniquely determined, and the joint distribution of X and Y is also uniquely determined if they are binary random variables. And this can be taken as a measure of similarity between these two random variables. If you prefer, sometimes you can speak about 1 minus this maximum probability, which is the minimal probability with which they can differ. And this is the total variation distance between these two random variables. So this is the measure that we are assigning to every pair of random variables that are answering the same question within the system when we take these two random variables in isolation. Then we are returning to the entire system, and we are creating the distributional copy of this system. It means that this thing now is referred to as a coupling of the random variables that are here. In the first row, these three random variables are distributed exactly the same as these three. These two are distributed as these two, and so on and so forth. So we have distributional copies. But in addition, we have all these S random variables jointly distributed, which is not true about the original system, obviously. And then we are asking the question, among all these couplings that we can always construct in an infinite number of ways, is there a coupling or some couplings in which any two same content random variables are as similar as they are in isolation? So for example, you take these two random variables again. These are the two copies of these two random variables. And within this overall coupling, there is some probability with which they coincide. And so the question now is this the same maximal probability that we have computed for these two when we have taken them in isolation? And if the answer is yes, then we say that the system is non-contextual. And if such a overall coupling cannot be constructed, then we say that the system is contextual. It is everything I really wanted to to recapitulate before I go to cyclic systems. Here, however, is some properties of non-contextuality and contextuality, and they are worthwhile mentioning because every reasonable theory of contextuality should satisfy them. Non-contextuality is preserved under extracting a subsystem. So a subsystem of a non-contextual system must be non-contextual. If you add or delete deterministic variables to or from a system, the contextuality should not change. Adding or deleting single variable contents or context also doesn't change contextuality. Coarse graining of the random variables does not change the contextuality, does not create a contextual system from a non-contextual, so non-contextuality is preserved. This will be spoken of in detail by Yana Koyala later. Contextuality and inconsistent connectedness or disturbance are logical orthogonal, so each of them can be present in the absence of the other. Non-contextuality of finite system is determined and measured by means of linear programming. So these are the main properties that I would like just to mention. By the way, in relation to the previous, to the talk given by Shane Mansfield, the analysis of contextuality here is automatically loophole free, in the sense that the inconsistent connectedness is built in within the analysis of contextuality. Also, the random variables can be results of sharp measurement or non-sharp measurements. And this makes absolutely no difference for the analysis itself at this level of generality. So these are cyclic systems. Cyclic systems are arranged in a cycle, as you see it this way. There are always two random variables within each context, and there are always two random variables within each content. So you have vertically aligned pairs and horizontally aligned pairs, and you see that they are forming this cycle. And this is just an example of a cyclic system of rank 4. It is describing the well-known EPR/BOM system that's usually known as Alice-Bob system. So it can be used for this purpose. This would be consistently connected if there is a space-like separation between the two particles. But you can also use the same system, mathematically the same system, to describe the two-slit experiment in quantum physics. This system will be inconsistently connected, and it's proved that it is non-contextual. It can be used also for things that are not even true random variables. For example, this is the quadruple version of the Liar paradox by Ubilitis, and in this case, random variables are simply answering the questions whether another random variable or another sentence in the same context is true or false. So the values of these random variables themselves can be considered as truth values. So here we have variables that are not random in the frequentist sense, but they are random in the sense of epistemic uncertainty, because we do not know which truth value to assign to each of them. And as a result, you can analyze this system in exactly the same way in which you analyze the Alice-Bob experiment. And in fact, it is a consistently connected system, but it deals with a completely different type of realities. So here are cyclic systems of rank 5, 4, 3, and 2. This system is never considered within physics, but it is quite prominent in behavioral sciences because it actually describes a very important so-called question order effect in decision-making area. And the prominence of these systems is obvious. Actually, a lot of effort was made actually to analyze this system. All Bell type of inequalities are derived for this type of systems. Usually, we have closed form inequalities for these systems, but generally we have to do linear programming without having these closed form inequalities. So the way we analyze the contextuality of cyclic systems is by presenting them in the forms of this vector of probabilities or expectations. So you have here expectations of one marginal, so just individual distributions, and you take the expected values of them. And then within each of the contexts, you can also take the expected value of the product, to which physicists sometimes refer to as correlations. So for the purposes of contextuality analysis, these individual expected values are uninformative in the sense that they are kind of setting the stage for the analysis of the pairwise relations or joint distributions. And so the way we will talk about these measures of contextuality in a moment is by fixing these values at the observed value. So let's say you have a particular system that you want to analyze, and it has particular values of these expectations. You are fixing them, and you are allowing the rest of these expectations vary. All the pairwise expectations vary. And in this way, you will be able to construct a body of all systems that would be non-contextual, and your system, if it is contextual, will be outside this body. This body is a polytope, and this polytope is completely characterized by us, and as a result, it is very easy to analyze it and to compute distances from a point representing your system and this polytope. The type of distance that we're using is the L1 distance, which sometimes is also referred to as city block metric. And it is simply the sum of the absolute values of the coordinate-wise differences. By the way, this is a particular measure of contextuality that I'm discussing. Within the framework of contextuality by default, we have defined 3 different measures of contextuality. And one of them, again, in relation to the discussions yesterday, one of them is actually is based on the constructing quasi-distribution and measuring the negative mass within this quasi-distribution. And interestingly enough, there is a generalized theorem that generalizes the theorem by Samson, Abramsky, and Brandenburger, namely that if you adopt the definition of contextuality and contextuality by default approach, then the system is contextual if and only if the quasi-distribution in the background has a negative mass. So it is again one-to-one thing, and you do not need consistent connectedness or non-disturbance to prove this theorem. But we are dealing now with a different measure, and the reason we are dealing with a different measure I will explain in a moment. So as you see here, this distance, as it is shown by these interrupted lines, is this measure of contextuality, here it is shown for the rank 2 system, which is much easier kind of to comprehend. Here is this polytope, and here is your system. It's outside the polytope, so it's contextual, and every point between this point and this point on this edge, so anything on this within this segment, is equidistant from your observed system. And so you can take a single coordinate difference, and it will be already the measure of the distance between the system and the polytope. It just happens that non-contextuality polytopes for cyclic systems have this very simple structure. They always create this pocket with which has the same legs. So the same it is an isosceles triangle here. So because of that, this value equals to this value, and every other straight line that you would draw from here to here will have the same L1 distance. And what is interesting that if you look now at the algebraic form of this distance, then this is the formula for this distance, and this formula can be understood in the very simple way. If you look at this value here, and if you assume that it is positive, so that the system is contextual, then we have the criterion of contextuality that has been derived a few years back by Jana Kujala and myself for all cyclic systems that are consistently or inconsistently connected. If it is consistently connected, then this part, total variation distance, disappears, and we have this inequality for contextuality, which is well familiar to most of us. So what is interesting is that the measure of contextuality is simply the difference between the left-hand side and the right-hand side of this inequality, with the coefficient which just depends on whether you are labeling the values of your variable 0, 1, or -1, +1. Here is the reason why I wanted to use this particular measure rather than some of the other measures that were proposed. It is the only measure that allows you also to measure the degree of non-contextuality. If your system is within the polytope, then you can also compute the L1 distance between this point and the contours of the polytope or faces of the polytope. and this would be a natural measure of non-contextuality of your system, how deeply non-contextual it is, or how easy, to disturb the system so that it becomes contextual. So this is the reason I use this particular measure. And again, it is the measure simply, again, the same formula, but taken with the minus sign. Of course, there is one slight kind of complication here, is that sometimes the distance can be, I forgot to tell you that this polytope is being circumscribed by box, and the values, the endpoints of the box are determined by the single variable expectations. So depending on how this box actually is superimposed on this polytope, because sometimes it's possible that the point within the polytope can be closer to the boundary of the box rather than to the actual boundary of the polytope itself. So in which case, we have a slightly more complex formula, but it is the only complication here. So we have been also interested in the question that is natural to ask, namely, if you take this box, as you see, this is the large cube that shows kind of logically possible values of your pairwise expectations. This smaller cube with smaller parallelepiped, so smaller box within this big cube, is determined by the single variable expectations, and within this parallelepiped, you have this polytope. And so, if you drop a point within this box, within the smaller box, what is the probability that you will hit a contextual system? So, in other words, if you are not guided by any theory and you are looking for a contextual system of a given format, for example, this is cyclic system of rank 3, how probable it is that you will hit a contextual system? Well, it turns out that we have a theorem here that gives you the upper bound for this probability. And this probability, this upper bound is this, and this value tends to 0 very fast. So you can see that depending on the rank of the system, rank 2, 3, 4, 5, you are essentially getting to zeros. So the probability that a randomly chosen cyclic system will be contextual is practically 0 for if you have many random variables involved, right? Which is probably more important outside quantum physics than inside, because outside quantum physics we usually look for contextual systems empirically by conducting experiments, rather than by being guided by a theory that tells us that certain values will be observed, certain values of the expectations of the pairwise products. And so it is interesting to notice that many attempts were made like this to find contextual systems. Practically all of these attempts failed, and this probably is an explanation for this, that if you are looking for a contextual system blindly, then the probability that you will find it is very small, unless you are dealing with very, very small systems. Okay, and another thing about the cyclic systems that I would like to mention is that they are important, as we have already seen. They cover a lot of empirical situations, and they can be used in variety of in a variety of empirical scenarios. However, they are not all important in the following sense. One might be tempted to say that if you have a large system, for example, this system is not cyclic, right? But it contains cyclic subsystems. So one might be tempted to conjecture that a system is contextual if and only if it has cyclic subsystem, a cyclic subsystem that's also contextual, right? Obviously, if it does have a cyclic subsystem, then that's contextual. Then the larger system must be contextual, right? So that has nothing to do with cyclicity. If a subsystem of a system is contextual, then the larger system is also contextual. However, well, the conjecture was that it might work also in the other direction, that if a large system is contextual, then it should contain a subsystem which is cyclic and also contextual. But it's not true. The counterexample constructed in this paper is here. It gives you particular system such that all of its cyclic subsystems are non-contextual, but the system itself is contextual. Right? Victor Cervantes will be talking today later, and he will be using this type of systems to justify the construction or to illustrate the construction of so-called hierarchical measure of contextuality. The measure that I'm considering, that I've just described for you, is a scalar measure. It is just a single number that gives you the degree of contextuality or degree of non-contextuality. And for cyclic systems, it's all that you need. But when you get to larger systems, sometimes it is more informative to look at contextuality hierarchically. So contextuality at level of pairs, contextuality at level of triples, and so on and so forth. And in this way, you can have different measures of contextuality and non-contextuality computed. So here is some literature that I placed here with clickable references so that you can easily look at some of the aspects of the things that I've mentioned. And that's all that I wanted to tell you today. I think I'm precisely at 25 minutes of my talk.
Okay, Ehtibar, thanks for this nice talk. I have a question. You mentioned that even if the system is consistently connected, will have a negative mass, like kind of negative probability. So the question is this valid only for cyclic systems, or you have a general proof?
Oh, no, it's a general proof for all systems. Yeah.
Great, thanks.
If you use this measure of contextuality based on a quasi-distribution, then the system is contextual if and only if you have negative mass there. Right. Completely general. Yeah.
Thanks.
I'll ask one. So this is a technical point I've been thinking about it lately. The polytope representation here is really useful, and it seems to me that it depends on the fact that you're representing things in terms of the product, the second moments. Because if you represent the distributions in terms of the raw joint probabilities, the space is not a polytope; it's not even convex. And so I'm wondering how general this trick is that you're using. Does it apply beyond cyclic systems?
So you are talking about representing the axis of this box, then would be probabilities rather than expectations. That's what you're asking.
Yeah, right.
No, it makes no difference actually. If you label your random variables 0, 1 rather than -1 + 1, then this expected value is simply the probability with which these two random variables both are equal to 1. And the same is true about other axes, obviously, right?
Yeah,
so
sure.
Actually probabilities.
No, I get.
And the measure actually is formulated in terms of these probabilities rather than expectations, because of which we have this 1/4, in front of these things.
Yeah, I get that. Sorry, let me clarify. So in the case where you have binary random variables and only 2 of them per context, then you're right. You can summarize the full joint distribution. And once you've already specified the single variable marginal, so you can specify the full joint distribution in either of the 2 ways you've just said. But that's not the case if you have, say, 3 observations, 3 measurements per context.
Right. It is a very good observation, and that's why there is a general measure CNT2 that was described in a paper that we published 2019, in which you have axes that contain pairwise expectation, triple-wise expectations, quadruple, and so on and so forth. But right now we are thinking in a different way. And again, Victor Cervantes will present his talk in which he would defend the idea of actually constructing a hierarchical measure. So you have separately, contextuality, non-contextuality measured for pairwise expectations, for triple expectations, for quadruples, and so on, so that you have a vector characterizing the type of contextuality in addition to just degree of contextuality, right? So that Victor will present in detail later on.